Hey everybody, I am here to make a video for you talking about force couple systems, just to reiterate this concept. So I'm going to do that mostly by going through an example, but I'll try and talk through some of the concepts here as we go. So in this example, we have a system. It's a cross section of a beam, and it has a 900 Newton force acting right here through the center, right here. Here we go. And then it has these two forces P, which are stated to be equal to 260 newtons. So I will write that on here for us. This is 260 and 260. And we would like to replace this force and couple system with a single force applied at point C. And you'll notice point C is here off of the body. And we need to also determine this distance X that C lies off of the body, okay? So a couple of things to reiterate here as we work. So what we're going to break this down into two steps to get to the final answer. In each step, we are going to be representing equivalent systems. Okay, so all of these are going to be equivalent systems. And what that means from a static and engineering statics point of view is that all three of these systems, I will label them here, system 1, system 2, and system 3, all three of these systems feel the same. They feel the same external forces and rotation of each other, but they get to it from a different representation of the forces. And we're going to sort of understand how this is an important concept as we move into module 3, when we start talking about how we support systems, how we secure them to their surroundings. Okay, so we want to create these systems that feel equivalent to each other so that everything internal, all of the particles internal, all of the connections that might happen, for example, here or here, or any deformation that might happen here or here is going to be the same in all three of these cases. Okay, so that's what makes the system equivalent. And again, from a statics point of view, we're looking at what's happening externally to the system. And so we're gonna view the equivalency from what we can control externally, okay? And so we need to think about this from two points of view. And those points of view are going to be total force. So this is our sum of our force equation. The sum of the forces in all of the system 1, system 2, and system 3 need to be the same. And then the total moment, or the total tendency to rotate. And so that's going to be the sum of the moments. Okay, so all three the same. Okay, so let's start by seeing how we can transition from 1 to 2, where in 2, what I'm going to represent is a force here and an external rotation. So think again about that torque, about that screwing in of the screwdriver. So it's going to be one force going down or up, we'll see which direction, and then one moment. Okay, so from 1 to 2, what does that force need to be, and what does that sort of torque rotation need to be to impart that same tendency to rotate for the entire system? If we look closely at system 1, we will see that the sum of the forces in the X is equal to 260 newtons going to the right. Let's say that going to the right is positive, minus 260 newtons going to the left, or 0. So we don't want any force in the X or Y direction on system 2, okay? Or if we do, it needs to be counteracted so that the sum is 0. The sum of the forces in the Y for body number 1 if I say positive is up, is negative 900 newtons. And so that's what we want to have in system 2. We still need to have the 900 newtons down. The sum of the moments on system 1, where let's say that counterclockwise is positive, is going to depend really what we're rotating about. So let's say that we're going to rotate right through the center, right at this point. Okay, and so that means that that 900 Newton force is not going to create any rotation because the line of action of that force is going through that point. However, the 260 newtons to the right and the 260 newtons to the left are going to try to cause rotation. And in fact, we know from our definition of a couple moment that that is a couple moment, right? It's so the moment is going to be F times D. It's going to be 260 newtons times that perpendicular distance between them, which is this distance here that I just drew in black. It's 0.180 meters. And so the moment that it feels is 46.8 Newton meters. So all of this is from system 1. And so when we look at system 2, we want to make sure that we have 900 newtons going down. So that's going to stay the same. We want to have a net force of 0 in the x direction. So I'm not going to draw any x forces. And then I want to feel a rotation of 46 Newton meters. And it is going clockwise. So I should have put a negative sign here. So I've drawn that in the correct direction on my number 2. And so that is 46.8 Newton meters. Okay, so let's step back here. In system 1, I had 900 newtons down applied at the center of the beam, which right between B and D. And I had these two forces going in opposite direction on the top and bottom that caused a moment, but no net force. When I went to number 2, I kept that 900 Newton force and I took away those two forces and I applied an external rotation. Those two systems are equivalent. All the particles in the cross section feel the same under both loading conditions. Okay, we're going to go one step further here, and we are going to move this 900 Newton force off of the actual cross section and see if we can still create an equivalent system. Okay, so there's going to be some distance here that it acts. Okay, so from 2 to 3, all of these things need to be the same. So this means this is still going to be 900 newtons down. But now we have to think about that rotation. And the interesting thing here is that a force acting a distance away from a body, from a point, is going to impart that rotation. And so what this distance that is not what I wanted to have happen. What this distance needs to do is it needs to cause that amount of rotation equal to the 46.8 Newton meters. Okay, so this 46.8 Newton meters needs to be equal to 900 newtons times some distance x. And so that x is equal to, if you solve it, you would get 0.052 meters, which is 5.2 millimeters. Okay, so this 900 Newton force acting 5.2 millimeters away from the body is going to again be an equivalent system. And there are ways we've represented this cross section, right, as two-dimensional, but you could imagine a system where there is a piece, maybe not on the cross section, and that's okay. There is a piece of the body that sticks out, and that is where that 900 Newton meters would act. Okay, I hope that this was helpful for you in thinking about how to represent equivalent systems. And let me know if you have any further questions on that. Thank you.